I'm really glad to be here. So I want to tell you a story today about symmetry and topology. Now, symmetry and topology are two of the conceptual pillars that underlie our understanding of physics and underlie our understanding of matter. And symmetry maybe is the most familiar concept that we might have to think about. And you know what symmetry is about, and I have to get used to using this. I will try. What symmetry is about is it's what you can what operations you can do to a system that keep it the same. Okay, and if you look at these pictures, you know, I love these pictures. You can imagine moving it over, it looks the same, or you can imagine rotating it by 90 degrees. And by understanding what things you can do to a system that keep it the same, that gives you a very deep understanding. And so in physics, this is an idea that we drive home from the very earliest days when we teach physics. So when we teach our freshman physics students how to analyze physics problems, what we tell them is the first thing you need to do is you need to understand the symmetries, because that can simplify your description of things. Now, there's a very a deep and powerful application of symmetry in physics, which is to use symmetry to classify phases of matter. And the simplest example of that is a crystalline phase, where you can understand that atoms in a crystal arrange themselves in a periodic, orderly fashion, which look kind of like these pictures, okay? And the atoms arrange themselves, and one can use symmetry to classify the different kinds of crystalline phases that matter can form. Okay, and so there's a very famous physicist named Landau who really built this concept of symmetry as a method for classifying the fundamental phases of matter. Now, symmetry is a very powerful tool, but there's another very powerful tool which is a little bit less familiar, at least in the elementary stages of studying physics, and that is the idea of topology. Now, what topology is about is it's about what is it that stays the same when you continuously deform an object. Okay, and so there's a classic picture for understanding what topology means, which is to imagine that you have a coffee cup and you have a donut. And what you can imagine in your mind is smoothly deforming this coffee cup. So I'm just taking little steps. It's staying pretty much the same at each step, but at each step along the way, it changes a little bit. And along the road, it ends up being a donut. Okay? And so this smooth deformation of the coffee cup keeps some things the same. Okay, so there's a sense, the fact that I can smoothly deform this, there's some sense in which these are the same. And one way of characterizing the sense in which they are the same is that they both have one hole in them. That's something that can't change as you smoothly deform this coffee cup into a donut. And so topology is a very deep idea in mathematics. And what I'd like to argue to you is that topology also plays a deep role in terms of distinguishing and classifying phases of matter. Now, the application of topology in physics is actually a very old idea. So physicists have been very interested in topology for decades. What is new in the last a decade or so has been a new appreciation of the interplay between symmetry and topology, and in particular for understanding the electronic phases of matter. Okay, and so that's the story that I want to tell you about today, is how it is that we can use these ideas in order to understand something very deep about the phases of matter that electronic materials can exhibit. Okay, so and one thing I will say is that the idea of topology is something that we've really celebrated in the last, a year ago. The Nobel Prize in Physics was awarded to David Thales, Duncan Haldane, and Michael Kosterlitz for their theoretical discoveries of topological phase transitions and topological phases of matter. Okay, and I will emphasize that this Nobel Prize was done for work that was done 30 years ago, understanding the role of topology in physics. And again, the thing that has happened since then has been this deeper appreciation of the interplay between symmetry and topology, and that's what I would like to describe to you. Okay, so I'm going to start off with some introduction and try to describe to you what topology has to do with electronic phases of matter. It's not immediately obvious that there's any connection at all, okay? And the connection comes through what's called the band theory of solids. And so I'm going to try to explain it in as simple terms as I can what the band theory of solids is and how topology has anything to do with that, okay? And then what I'd like to describe to you is some of the topological electronic phases of matter that we've come to understand over the last decade, in particular topological insulators in 2- and 3-dimensional materials, and then topological superconductivity, which is an idea that we think may play a role in ultimately making a new kind of computer. Okay, and so after this, then I'll try at the end to give a little bit of a feeling for where we stand at the moment and where this field is heading into the future. Okay, so now so my contributions in this area all started off about maybe 12 years ago. In a collaboration with my colleague Jean Malie at the University of Pennsylvania. So I'd really like to highlight Jean Malie. Over the years, I was joined by a number of students and postdocs and colleagues, and one in particular I would like to highlight is Liang Fu, who in the very early stages of this work played a really foundational role in the progress that we made. Okay, so I want to tell you about electronic phases of matter. And so what I want to start with is the most basic electronic phase of matter, and that is the insulating state. So you know what an insulator is. An insulator is something that does not conduct electricity. Now, you might say that the insulating state is the most boring state of matter because it's the state in which the electrons do nothing. They just sit where they are. And now we teach our beginning physics students about insulators. In fact, this year I'm teaching a course for freshman physics students on the theory of electromagnetism. And so I tell them what an insulator is. And what I tell the freshman students is that an insulator is a material. It's made out of, it has electrons and protons in it, but the electrons are sort of bound to the atoms, and so they're stuck and they can't go anywhere, okay, because they're stuck on their home atom. Now, so that's true. But there's one thing that I don't tell the freshmen, at least not immediately, is that actually, in order to understand why this is true, you really have to understand, it really follows from quantum mechanics, okay? And so here's the thing. So in quantum mechanics, what quantum mechanics teaches you, the theory of quantum mechanics, is if you have a motion that goes around in a periodic orbit, so the electrons are going around in an atom, sort of the way planets go around the solar system, okay, in a periodic orbit. And what quantum mechanics teaches us is that when you have a periodic orbit, the energy levels that the electrons can only have discrete values. And so, and in chemistry, we call these discrete energy levels, we call them orbitals. Okay, and so what happens in a system of inert atoms is that you have orbitals that the electrons can exist in on each of the atoms, and all of the occupied orbitals are separated by a huge energy gap from the orbitals that are empty. So in order for the electrons to do anything, they have to be able to overcome this very large energy gap. Okay, and so it's for that reason that electrons in an electrical insulator are inert. They just don't do anything. Okay. So as I said, insulators maybe are boring, but I want to convince you that they're actually not quite as boring as you might as that sounds. Okay, because things get a little bit more interesting. So this is like, I imagine I have a crystal of inert atoms that are really not talking to each other at all. Things get more interesting if you bring them closer together, so that they start forming chemical bonds with one another. Okay, and in particular, as you bring the atoms together, they start interacting, and so one can ask, how can one describe what's going on in such a covalently bonded crystal? And the language, this was the language for how one describes this was one of the greatest triumphs of quantum theory in the last century. Okay, and this language is what has become known as the band theory of solids. Okay, and so the idea of band theory is that when you bring the atoms closer together, so that they're starting to interact with each other, then these states, these orbitals on the atoms, they sort of broaden out into bands. And so, but the thing that happens is that the band of occupied states remains separated by an energy gap from the empty states. Okay, and so this is the essence of a insulator that we get in band theory. Now, the band theory of solids, I think, is probably one of the most consequential theories in physics that we have. Okay, it's the because and by using quantum mechanics, one can come up with a very detailed understanding of the structure of these electronic states that form an insulator. Okay, and so one has a very deep understanding, and this deep understanding of the electronic structure of these materials forms the basis for our understanding of all kinds of electronic materials. Okay, the electronic materials that are in this laser pointer, the electronic materials that are in your cell phone in your pocket or your computer, those are semiconductors. Okay, ultimately the information technology that we've all grown accustomed to derives from the understanding of electronic materials that comes out of the band theory of solids. Okay, and so band theory is a big deal. Now, there's a point that I want to make, though. Okay, which is so this looks kind of complicated. Okay, so there's lots of details to understanding the specifics of specific materials. Okay, but there's a sense in which this complicated electronic structure is kind of like this simple, inert atomic insulator. Okay, in the following sense, in the sense of topology that I introduced at the beginning. Because what you can imagine is starting with this and very smoothly and slowly, making the atoms get further and further apart. And as you do that, what's going to happen is this energy gap, it'll get bigger, and one can smoothly interpolate between this complicated electronic structure, and when you've pulled them apart, it looks like an atomic insulator. And along the way, nothing drastic happens along the way. And in particular, this energy gap, which is responsible for the material being inert, remains finite. Okay, so there's a sense in which the covalent insulator is kind of the same as a atomic insulator. Actually, there's a sense in which they're kind of the same as the vacuum, where there's nothing, right? The vacuum actually is not quite as empty as you might first have thought. If you think in terms of the relativistic theory of quantum mechanics, this is the Dirac's theory of quantum mechanics, then the vacuum has a valence band of occupied states too. Okay, now this valence band for the vacuum, if I remove a particle from this occupied state, what that really means is that I've created the antiparticle of an electron, which is called a positron. Okay, and so Dirac discovered that that you can have a positron, which is really the same as removing an electron from an occupied state of a valence band. Okay, so the vacuum has a valence band too. The only difference is that this energy gap in the vacuum is 1,000,000 times bigger. Okay, so there's a sense in which all three of these are the same. Okay, and so I would like to elevate this principle of them being, this idea that they're the same, into a principle, okay? And so this principle I'd like to call the principle of adiabatic continuity, okay? So the idea is the following. I want to argue that insulators which are, inert, electrically inert materials, are topologically equivalent if they can be smoothly deformed into one another without closing this energy gap, which is responsible for the fact that they're insulators. Okay, and so that gives this idea of topological equivalence between different kinds of materials, Things can be either the same. Now, this poses an interesting question, because if we can talk about whether things are the same, then you can ask the question, could they be different? Okay, so let's think in pictures. So a sphere and a bowl, they're kind of the same. You can imagine smoothly deforming a sphere and squashing it down, and nothing drastic happens to get to a bowl. There are no holes. In this case, we call this genus 0. Okay? So in a sense, an insulator is kind of like this. So the question you can ask is there any analog of the donut for an electronic material? Okay? Because, there's no way you can get from a sphere to a donut without, poking a hole in it, and that's against the rules. Okay? So here's the thing. The answer to this question, remarkably, is yes. There do exist electronic materials that are insulators. They have an energy gap, but there's no way that you can continuously deform them into the atomic insulator or the vacuum. Okay? And so these topological electronic phases are fascinating states of matter, and they're the phases that I want to introduce you to. Okay? Now, the original topological state, the one that we understand the best, the one that we understood first, is called the quantum Hall state. And so let me try to explain to you what that is. So the quantum Hall state arises when you confine electrons to a two-dimensional plane. Okay, and so this two-dimensional plane could be the interface between two different materials. Okay, it could be a planar interface between two different semiconductors, for example. Okay, and you can arrange it so that there are electrons which can only live in that plane. And so what one does is one puts this two-dimensional plane of electrons in a big magnet. Okay, and what electrons will want to do in a magnetic field is they want to go around in circles. This is what electrons do. Okay, so this motion, this circular motion of electrons in a magnetic field, is called cyclotron motion. And this is just what electrons do. Now, the thing is, though, this circular motion of the cyclotron motion, it's kind of like the motion of electrons going around in an atom, right? In an atom, it's like a solar system that's going around in a circle. Likewise, this cyclotron motion is the electrons going around in circles. It's executing a periodic circular motion. And remember what I told you, that quantum mechanics requires that when you have periodic motions, you can only have discrete quantized energies. Okay, so it's the same story where one has discrete quantized energies, and in this cyclotron motion, we call these energy levels Landau levels, okay, after the same Landau that I told you about before. Okay, and so you can have an interesting situation where you have, just like in an atom, you have some number of these Landau levels are occupied by electrons and separated by a big energy gap from the Landau levels that are empty. Okay, and so this situation, it's going to be like an insulator. It's going to be electrically inert for the same reason, because to do anything, in order for the electrons to do anything, they have to overcome this big energy gap. Okay, so it's like an insulator, but actually it's not quite an insulator, okay, because of the following thing. If you were to take this material and you were to hook it up to a battery, okay, so that means you apply a voltage. That's what a battery does, gives you a voltage, or another way of saying it is you're applying an electric field. That's what happens in a battery, okay? The electrons are going around in these circles. If you apply an electric field going up, then it turns out these cyclotron orbits will drift and move perpendicular to the electric field, okay? And that introduces an electric current. So it's not an insulator, okay? There is an electric current flowing, and so it's not an insulator. So what happens, you apply an electric field, you get a current perpendicular. So this gives rise to a phenomenon that's called the Hall effect. Okay, that's when you have a current that flows. It's not flowing in the direction the battery's trying to get it to flow in. It's flowing perpendicular. Okay, and now the thing that's remarkable about this, okay, so this is something that you can measure in the lab. And if you measure the current in response to the electric field that you apply, that defines a kind of what's called a conductivity. And if you measure that, then what you find, the value that you measure, as a function of the magnetic field, it sort of looks like this red line. It has these steps, and these steps occur at very precisely defined values of the electrical conductivity. In particular, this conductivity is an integer multiple of this combination of fundamental constants. This is the charge of an electron. This is a constant called Planck's constant, a fundamental constant in quantum theory. And this integer, so these are numbers that we know. They're fundamental constants. We know them to great accuracy. You measure the conductance of this thing, and what you find is that the answer you get is a multiple of this combination of constants, and that multiple you can measure to 1 part in a billion. Okay, so this so if you want to think of this as a way of measuring this combination E squared over H, you can measure it to huge accuracy. Okay, so something very deep is going on here. It's not an insulator though. Okay, because there's an electrical current flow. So the question that this poses is what's the difference between these? Okay, because both of them should be insulators. What's the difference between this and the trivial insulator where I'm occupying the energy levels of atoms? Okay, so what's the difference? And so the difference is a matter of topology. Okay, and so I think the first person to really understand this difference is one of my biggest heroes in theoretical physics. His name is David Thales. So David Thales, so this insight is one of the things that David Thales got the Nobel Prize for last year. Okay, and so what Thales realized is that this distinction between a conventional insulator, okay, this is just the electrons bound to their home atoms, and this quantum Hall state is a topological property of the band structure. So when you have a so we can characterize the band structure when we have an energy gap. We can characterize the occupied states in the valence band, if you will. We can think of them as being a function of a momentum k, and those can be classified by what we call an integer topological invariant. Okay, and so I wrote down a formula for what this integer topological invariant. It's called a Chern number. Okay, if this kind of formula speaks to you, then that's good. If it doesn't, then that's okay. I'm not going to have lots of formulas like this. Let me just to those of you who this formula doesn't speak to, let me just quote one of my physics teachers when I was in college, and he was trying to tell us something that was sort of a bit beyond where we were at the time. And what he said to us is that really it's not difficult, it's not hard, it's just a little bit more advanced. And so it's kind of like that with this. So this is actually something which is very simple, if you're at the right level. And so let me try to give you an idea of just how simple it is. So what it's kind of like is it's kind of like a winding number. So imagine that you have a rubber band which can wrap around a pole. Imagine you have a pole coming out like this, and you can wrap the rubber band. So here it's not wrapped around at all. Here it's wrapped around once, or it could be wrapped around twice. It could be wrapped around any integer number of times. Now the thing about this wrapping number is that I can change exactly where the rubber band is, but I can't change the wrapping number without cutting the rubber band open. Cutting the rubber band open and then gluing it back together again. Okay, so this winding number is a topological invariant, and so the Chern number is really the same kind of thing. It's just what it's doing is it's describing the way in which the quantum state sort of wraps around as a function of momentum. Okay, and so this integer quantum, this integer topological invariant is the thing that distinguishes the trivial insulator from this quantum Hall state. And so what Thales proved is that this integer, this topological invariant n, is precisely the thing that you measure when you measure this quantized Hall conductivity. So in a sense, the fact that you can measure this thing to this ungodly accuracy, to 1 part in a billion, it's because you're measuring a topological invariant. Okay, and so as I said, this was one of the insights that earned David Thales the Nobel Prize. Okay, so now you can ask the question. Okay, so we have so this quantum Hall state is different than the insulator. So, but what consequence does that difference have? Okay, and so let me try to explain to you what the most interesting consequence of this is. Okay, and this consequence was first really understood by another one of my heroes in theoretical physics named Bert Halperin. And so the point is to consider what happens if you have if your system that has your two-dimensional electrons has an edge. So there's like a wall that the electrons can't go past. And so remember, so this is kind of easy to think about if we think about this simple cyclotron motion picture where the electrons are going around in circles. Because if the electrons are going around in circles, if there's a wall, then when the electrons are going around in circles, they can sort of bounce off the wall. And when they bounce off the wall, then they execute a kind of interesting kind of motion. Because notice that along this wall, it's only going from left to right. Okay, so this edge is kind of like a one-way street for the electrons. Okay, they can't go backwards; they only go forwards. Now, so this is what you get in this simple, sort of kind of classical picture of electron motion. One can also understand this motion in the context of quantum theory. Okay, and in quantum mechanics, we give these one-way edge states a fancy name. We call them one-dimensional chiral Dirac fermions. Okay, so that's a bit of a mouthful. But what it means is it's just these electronic states that can only propagate in one direction. Okay, and the thing is, and so if you think about in terms of the energy levels, then basically we have the occupied states that form the valence band, the empty states that form the conduction band. Along the edge, there's a band of states that connects the two. Okay, and the thing is that band of states has to be there. Okay, and so the fact that these states have to be there is something that one can understand on many, many, many different levels. Okay, for me, I kind of like the cartoon level. That's where I sort of feel like I can understand. This picture I understand pretty well. But there are many, many more levels of sophisticated understanding that one can understand this. And so I'd like to elevate it to a principle which I'll call the bulk boundary correspondence, okay? Where if you have a topological invariant that characterizes the interior of your system, okay, so it's 0 if it's a trivial insulator, or it could be 1 or 2, then that has to be equal to something that characterizes the boundary, which is the number of these chiral edge modes. Okay? And as I said, this theorem can be understood on many levels. Ultimately, in mathematics, it's related to some very deep index theorems. Okay? And it's something which is not unrelated to the kind of mathematics that Jim Simons invented. Okay, so this is the bulk boundary correspondence, but I want to say something about these edge states because they're really rather magical things. Okay, they have to be there. You can't get rid of them, and moreover, the electrical current flows without dissipation. So let me if you're an electron. Imagine you're an electron. You're in one of these states, okay? Well, you have no choice but to go forward. That's the only thing you can do, okay? Which means that, if you put in an electron over here, with 100% certainty that it's going to come out over here, okay? That's not the way ordinary conductors work. In ordinary conductors, the electrons are bouncing around. They can go this way and that way. This one is a very organized flow of electrons. It has 100% transmission probability. And this perfect 100% transmission, that really underlies the fact that you can measure this Hall conductance to 1 part in a billion. It's that perfect transmission. Okay? And moreover, you don't need to have a perfect system. Okay, you can have, it doesn't need to be a perfect crystal where everything is perfectly ordered. You can have disorder. It can be all messed up. Okay? Because if there's an impurity here, an electron's coming along, it's not going to bounce back. It's just going to go around. Okay? And so this means that you can measure this perfect conductance in an imperfect sample. Okay? So that is one of the powers of this topological robustness, is that it doesn't have to be perfect. Okay, it's forgiving in that regard. Okay, so now so you might think that having this very organized flow of electrons has got to be useful for something, right? Because think one of the problems that you have with your computer, if your laptop, is that it gets hot. Okay, so when you run currents through conductors, they tend to heat up. Okay, and so wouldn't it be nice to be able to have your electrons flow without any dissipation? Okay, now there's a little bit of a problem here, at least for this version of it, which is that in order to make this happen, I told you had to put it in a big magnet, a big electromagnet. Okay, and that's not such a convenient thing to do. You don't want to have a big electromagnet in your pocket with your cell phone, right? So, so one can ask the question whether there's anything else you can do. Okay, and in order to do that, I want to think about what it means to have this magnetic field, and I want to think about a little bit about symmetry. Because imagine, imagine what would happen if you imagine this motion. Imagine you take a motion picture of this motion, and then you play the motion picture backwards. Okay? If you were to do that, then it would look different. Then it would flow back this way. Okay? And so what I want to think about is I want to think about what happens if I run the motion picture backwards. And this leads me into the idea of a kind of symmetry, which, I want to talk about symmetry now. But this is maybe a little bit less familiar symmetry than like a rotation or a translation symmetry. Okay, and so what time reversal symmetry is about is it's about the question: if you take a motion picture and you run it backwards, does what you see in the backwards motion picture obey the laws of physics? Okay, now actually the fundamental laws of physics do obey, are the same if you run the motion picture backwards. Okay, but actually a magnetic field breaks that. Okay, because if you think about it, a magnetic field. How do you make a magnetic field? Well, you make a magnetic field with an electromagnet. And what an electromagnet is it's basically just a coil of wire that you can pass an electric current through. So if you run the motion picture backwards, then the current goes the other direction because everything's going backwards, and so the magnetic field is odd, changes sign. Okay, so a magnetic field is odd under reversing time. Okay, likewise these edge states, an edge state which moves from left to right, if I run it backwards, becomes an edge state that moves from right to left. Okay, and so it kind of makes sense that you need to have something, so in order to have these one-way edge states, you have to break this time reversal symmetry. Okay, which means that you have to put it in a big magnet. Okay, now there's one other feature of this that I want to mention, which is a unique property of quantum mechanics, which has to do with spin. Now, an electron, it's not quite as, it has a little bit more structure than you might first have thought. So an electron, it's not just a point particle. Really, it's like a little bar magnet. So an electron has an intrinsic property which we call spin, which is you can think of it as like a spinning top. Okay? And basically there are two kinds of electrons. There are electrons that are spinning up, and there's electrons that are spinning down. And you can ask the question, well, if you run the motion picture backwards, what happens? Okay? And so it makes sense that since the spin is sort of like a spinning top, that if I run the motion picture backwards, it's gonna flip. Okay, but it's very interesting to see how this fact is implemented in quantum theory. And so let me just tell you something here. So in quantum mechanics, running the motion picture backwards does two things. Okay, one thing it does is it gives this little star here. Okay, and if you know what the star means, then good. But if you don't, it doesn't matter. Okay, but the other thing that it does is it gives you this minus sign. Okay. Now, so I teach quantum mechanics to first-year graduate students sometimes, and what I always tell them is I tell them that this is my favorite minus sign. So magical consequences happen because of this minus sign, and very important developments in my career have happened because of this minus sign. So what this minus sign tells you is that if you do time reversal twice, then you get a minus sign. Okay, and this fact has a deceptively simple consequence. It's very deep, but very deceptively simple consequence, which is called Kramer's theorem. And what this consequence is that if you have these electrons and you have symmetry under the reversal of time, there's no magnetic field, then every state has to be at least, has to have a partner that has exactly the same energy. So you know, I told you that electrons can exist in these discrete energy levels, but they have to come in pairs. Everyone has a partner at exactly the same energy. Okay, and this fact is responsible for the fact that you can have topological insulators. So you can ask the question. So I told you that this quantum Hall state, which has these magical edge states, it requires a big magnetic field. It requires that you have a broken time reversal symmetry, okay? But you can ask, well, what if you have unbroken time reversal symmetry? So you have no magnetic field. Could there be is there anything left? Okay, and so this is where the more recent developments come into play. So in fact, there is something left when you do have time reversal symmetry. And so let me try to describe to you a little bit what that is about. So the simplest version of this, which is the first version that we came up with, and it was really, we were sort of just playing around, trying to think about things, and we came up with a toy model. Okay, a toy model is just, it's a model which is not trying to describe any particular system in any detail, but it's a model that is simple enough that we can think about and try to understand. Okay, and what we considered was the following situation. So you know, this quantum Hall effect, you know, if we run the motion picture in reverse, you know, it obviously looks different. So what I can do, let's consider two copies of this quantum Hall effect, one for the up spins and another one for the down spins. Okay? So if I do that, because remember, when I run the motion picture in reverse, the up spin turns into a down spin. And so if I have the up spins and the down spins going in opposite directions, then when I run the motion picture backwards, it looks the same. Okay? So this this system, which is sort of what it is it's two copies of the quantum Hall state, does respect time reversal. And it's even better than that. Time reversal symmetry actually protects these edge states in the following sense, that these edge states, they have to cross each other, and this crossing is something that is protected because of time reversal symmetry. Okay, and so what this told us is that as a matter of principle, it is possible to have an electronic state that will be guaranteed to have these conducting edge states on its boundary. Okay, and so now you can ask the question, well, how can you go about convincing nature to do this? Okay, and so our first idea was actually kind of unrealistic. Okay, but shortly afterwards, Shucheng Zhang and his collaborators came up with a brilliant idea, which was to consider a structure made out of a well-known semiconductor called mercury cadmium telluride. Okay, so mercury cadmium telluride is something that it's been around for a long time, and it's something it's a material that has been very well studied. But nobody had ever looked at it in this way before. Okay, and so what they predicted is that if you make a little sandwich where you have mercury telluride sandwiched between mercury cadmium telluride, then this two-dimensional, inside of the sandwich exhibits the same quantum spin Hall state. And the prediction then is that it has these conducting edge states on its boundary. And so this was a theoretical prediction, and within a year, Lawrence Molenkamp and his collaborators in Würzburg, Germany, had built these structures. They built devices made out of mercury telluride and performed the electrical measurements which demonstrated that indeed these conducting channels at the boundary are there. Okay, and so this was the first demonstration that you can have a topological phase of matter that's not the quantum Hall effect, something that you can have without having a big electromagnet. Okay, and so this was something that sort of really sort of launched this new field in physics, that's been devoted to studying the topological phases of matter. Okay, so this is sort of the simplest version of this, which occurs in a two-dimensional plane. You can ask the question, what if you have a three-dimensional piece of material? It's like a three-dimensional rock, a piece of stuff, okay, which you can hold in your hand. Could that be a topological insulator? So in particular, you could ask the question, you have an insulator on the interior, okay? A three-dimensional topological insulator is an insulator on the interior, but it is guaranteed to have a conducting surface on every boundary. Okay, so rather than having the edge of a two-dimensional strip, you can have the surface of a three-dimensional volume. Okay, and so in fact, so we realized that this was possible, and realized that these conducting surface states are something which have a very special property, which is impossible to have unless it's on the surface of a topological insulator. Okay, and so what we call these surfaces, they have what we call a surface Dirac cone. I don't want to explain too much what exactly this means, but this is a very, very special kind of electronic structure that the electronic states on the surface have, and it's guaranteed that you can't get rid of them. Okay, now so we have this idea, and again, the way this proceeded, it's actually a little bit different than the way things usually proceed in physics. The way things usually proceed in physics is that people who are doing experiments do some measurement that they don't understand. And then some understanding develops, and one develops theories to explain the experiment. This really occurred rather differently in that the concept of these topological insulators sort of emerged out of kind of pure thought. And we realized by thinking about the theory that they were in principle possible. And then we worked very hard to try to make these theoretical ideas come to life by thinking about real materials where they could occur. Okay, and there are many. So one of the nicest ones is a material called bismuth selenide. So this is bismuth atoms and selenium atoms, and this is another. It's actually a well-known material. It's been studied for decades. It's actually very well known for its thermoelectric properties. So it's useful for coolants. Okay, and so this is a material which it's an insulator. It has a energy gap in its bulk. It's actually a pretty good insulator. If you probe the surface states, so what I'm showing here is a picture that was taken by Zahid Hassan from Princeton University, and what he does is he basically takes a fancy picture of the surface, which allows him to probe the electronic structure of the surface states, and what he sees here is basically a textbook perfect Dirac cone. Okay, and so this observation demonstrated that this three-dimensional topological phase really is something that one can create and one can study in the laboratory. And so in the years since this was discovered, there's a whole industry of learning of different kinds of materials and different kinds of experimental probes that one can do to understand these materials. Okay. Now, so you can ask, well, so what kinds of things might you be able to do with it? And let me just give a little bit of a flavor of what you might be able to do. So let's not worry about this one up here. So what you might be able to do if you have this three-dimensional topological insulator. So you have these protected surface states, but and these protected surface states are guaranteed to be there as long as you don't break, as long as you don't include a magnetic field, as long as you don't break the symmetry under time reversal. Okay. Now, of course, if you put in a magnetic field, then all bets are off. Okay. But it turns out that one can use these materials as a route to orchestrating more interesting configurations of states. So in particular, one thing that you could do is you could put a magnetic material, put something like a bar magnet on the top and a bar magnet over here. And if you do this correctly, then what you can arrange is that on this channel of the surface in between, that you have precisely one of these one-way edge states that's just like the edge state that we had in the quantum Hall effect. Okay? So here, if we can do this, then this is a way of accomplishing this one-way perfect conductor, which with dissipationless flow of electrons. That's a way of accomplishing that without having to use this huge electromagnet to make it happen. Okay, and so this is something that one could hope for. Now, so this is one kind of direction that one can use to sort of leverage these topological surface states that these topological insulators have. So I'd like to describe to you another more ambitious thing that you might be able to do with these topological insulator surface states, which is to find another way of destroying them. Okay, so it turns out that so we can get rid of the surface states if we include magnetism, a magnetic field that breaks the time reversal symmetry. It turns out there's another symmetry that one can break, and this has a fancier name. It's called gauge symmetry. But what it means is that you can, if you put another kind of material which is called a superconductor in contact with this surface, then it does something very interesting to the surface states, okay? And what I want to argue to you is that it's a route to engineering topological superconductivity using ordinary superconductors. And so what I want to explain to you in the last, 5 minutes or so is I want to explain to you another fundamental electronic phase of matter, which is called a topological superconductor, and try to get across why it is that this is something that we very badly would like to make come to life in the real world. So I can't, at this late hour, I can't give you a whole course on superconductivity. I'm not going to try to do that. But what I can do is I can tell you that a superconductor is kind of like an insulator in the following sense. It has a conduction band and a valence band that are separated by an energy gap, just like an insulator. Okay. But there's a price that you have to pay for this simple-minded picture of a superconductor, which is that actually there is an intrinsic symmetry that relates the conduction band to the valence band. Okay. And moreover, if I have an extra electron in the conduction band, that's really the same state as removing an electron from the valence band. Okay, and so that's a price that you have to pay for this sort of semiconductor interpretation of the electronic structure of a superconductor. But once you accept that, then you can do exactly the same kind of analysis of a superconductor as we do to analyze an insulator. Okay, so you can ask the question, could there be topological band structures to the superconductor which might have some topological edge or surface states? Okay, and so the simplest version of this for a superconductor is actually what happens if you have a one-dimensional superconductor. So imagine that you have electrons which are just confined to move in one dimension, so they're like on a line. Okay, so then you can ask the question, well, if I'm at the end of the line, you could imagine that you could have states which, and we have an energy gap like in an insulator. You could imagine that there could be states which are sort of localized near the end, but have an energy which is sort of inside this energy gap. Okay, now because of this intrinsic symmetry, if you have a state at energy E, then it has to have a partner at energy minus E. Okay, so that has to be the case. Okay? Unless you have a state that is exactly at E equals 0. Because then, if it's at E equals 0, then it's its own partner. Okay? And you see, if you have this, then it's impossible to get rid of it. Because how could you get rid of it if you tried to move it away from 0? Well, then its partner would have to appear out of nowhere. And that's against the rules. Okay? So this zero energy state is topologically protected in the same way that the chiral edge states in the quantum Hall effect are topologically protected. Okay? And so what is it about this one-dimensional system that makes it have this zero mode at the end? Well, that's what happens at the end of a one-dimensional topological superconductor. Okay? Now, so these zero modes at the end are actually even more interesting than this, because remember I told you that there's this redundancy where adding an electron at E is the same thing as removing an electron at minus E. Well, that means if the energy is equal to 0, then that adding an electron to this zero mode does exactly the same thing as removing an electron. Now, you could ask the question, how could that possibly be? You know, adding an electron does the same thing as removing. The thing is, in a superconductor, what you're allowed to do is you're allowed to give away a pair of electrons for free. That's how that can happen. Okay. Now, this state it's almost like half of a state. Okay, and it's something that we call a Majorana fermion bound state. Now, Majorana. So I want to say just a few words about Majorana. So Majorana was a very curious character in the history of physics. So he was around in the early part of the 20th century. He was a genius, at least if you believe Enrico Fermi, who's one of the grandfathers of quantum theory. Okay, but he had a tragically short career. Now, so Majorana was around in the days when Dirac introduced his unification of quantum mechanics with the theory of relativity. Okay? And what Majorana realized is a consistent interpretation of Dirac's equation is that it is possible for a spin-a-half particle to be its own antiparticle. Okay? So this means, you know, what does it mean to have an antiparticle? If you have a particle and an antiparticle, they can come together and poof, they disappear. Okay? If a particle is its own antiparticle, then you have two of the particles that are the same, they come together and poof, they disappear. Okay? And so Majorana realized that this was possible. Okay? Now at the time, this was just sort of, well, in principle, this could happen idea. Okay? But it was a brilliant idea. But shortly after he had this idea, he got on a boat in Italy and disappeared off the face of the earth. Nobody knows what happened to him. So he's gone. Now, actually, a little bit more recently, there is a little bit of news. Now, there's a star. I always have to put this little star here. What that star means is if you believe what you read on the internet. So if you believe what you read on the internet, then actually the Italian police, in this decade, concluded that actually Majorana was alive and well in Venezuela up until the 1950s. Evidently, there's some photograph that they think is Majorana. Okay, I don't know whether this is true or not. Okay, but one thing I do know is that observation of Majorana's fermion is one of the great challenges in physics today. Okay. Now, you see, there are actually several venues where this could happen. One of them is fundamental physics. You know, actually, fundamental particles could be Majorana fermions. They could be their own antiparticles. In particular, the neutrino is a particle that might be a Majorana fermion, and there are active experiments going on today in high-energy physics to try to determine whether or not that's the case. That's one of the burning questions. Okay. Now, in condensed matter physics, we're interested in a little bit different situation, and I want to try to convince you why it is that we are so excited about having a Majorana fermion in condensed matter physics. And the reason that we're so excited about this is due to an insight due to a modern day genius named Alexei Kitaev, who had this insight that if you could have these Majorana zero-mode states, then you can have a new way for storing and manipulating quantum information. Okay? Now, so here's the idea. If you have two of these Majorana zero modes, two Majorana zero modes define a single quantum bit. A single bit so a bit is how computers store information, a 1 or a 0. And in quantum mechanics, you can have a 1 or a 0 or a kind of funny combination between the two. Okay? Now, and so a quantum computer is something that would then, operate on these qubits. Now, what Kitaev realized is that if you have two of these Majorana modes, they define a single qubit. Okay? And the beauty of it is that the information that's stored in that qubit is stored non-locally. It's stored sort of in two different places, which means if you look over here, there's no way that you can tell what the state of that qubit is. And if you look over here, you can't tell. And that's great, because the whole problem with making a quantum computer is how do you keep the quantum computer from accidentally measuring itself? Okay? Because if you measure a state, you kill it. Okay? And so that's the fundamental challenge for making a quantum computer. And so Kitaev's insight says that if you could have a topological phase with Majorana fermions, then that gives you a route to possibly being able to overcome that problem. Okay? So in any case, so that's the reason what we would really very badly like to have this happen. And I'm running out of time, so I want to just, I'm going to flash some pictures. This is something which is very active area in both theoretical and experimental physics. There are a number of experiments that are very promising evidence that we may actually have the Majorana bound states at our disposal. Okay, and I don't think we don't have the final word about this, and there's many challenges that have yet to be overcome. But this is a very exciting time to be a condensed matter physicist, because there's really a lot going on. And so let me just close by trying to give you a little bit of a flavor for what is coming. And the way I see it, there's sort of two ways you can go. Okay, in this field of topological electronic phases of matter. So one way you could go is that there are many more examples of topological band phenomena, things where you have energy bands, the band theory of solids, and the energy bands have some topological features in them, especially when you combine it with symmetry. Okay, and let me just give you an example of that. So an example of that would be what I'll call symmetry-protected topological semimetals. And so these are materials that have topological features in their electronic structure. The most famous one of these is a material called graphene. Okay, so maybe you've heard of graphene. It's the material that's like a single plane of pencil lead. Okay, and the thing that makes graphene interesting from an electronic point of view, it has a conduction band and has a valence band, but they just barely touch each other at these single points, which are these Dirac points that are kind of like the Dirac points that we have at the surface of a topological insulator. Okay, and the thing is that what these Dirac points are protected by, they're protected by a combination of topology and symmetry. Okay, and so this is something where there are many more examples of this kind of thing, and there's a huge amount of progress that is being made understanding the electronic structures of real materials, where one can model them computationally, one can do experiments, and one can understand their topological structures. And so there's a huge interplay that's going on, and there are many versions of this. Now, there's another direction that you can go, and this will be my last slide, which is a more ambitious direction, which is to consider electronic states that cannot be described within the band theory of solids. Now, band theory is great. So when band theory works, it works really well. Okay, but it doesn't always work. Okay, and the cases where it doesn't work can be much more interesting than the cases where it does work. Okay, and so in fact, so many very exotic things can happen. You can have situations where you have excitations of your material that are just like particles. They behave like particles, but they have a charge which is 1/3 of the charge of an electron. Okay, and we know that these kinds of things can happen, and so the question is whether we can the reason we know this is because of a phase of matter called the fractional quantum Hall effect, which is sort of a cousin of the quantum Hall effect that I introduced to you earlier. Okay, and this is something we know quite well. The question is, can we do for the fractional quantum Hall effect what we did for the integer quantum Hall effect in topological insulators? And so there are many very, very exciting things that one might be able to think about. And so this is another direction where there's been a huge amount of progress. In this theory, in this case, though, the progress has mostly been on the level of rather abstract theory. Okay, and so there's much more work that we need to be able to do in order to figure out how to make these kinds of exotic topological states sort of come to life in the real world. And so that's one of the driving things that drives me these days. Okay, so I think I'm going to finish up. I'm running a little bit late, and so just finish with the idea that symmetry and topology are two big ideas. Right, and they fit together and form a sort of a beautiful structure that we can use to understand the electronic properties of materials. And there are many challenges that we face in our field. And again, let me just say this is a great time to be a condensed matter physicist, because there's really a lot going on. So thank you so much.